the start. I hope he doesn't mind. Good morning. Nice to see you back. Do you have any questions or comments regarding the things that we discussed yesterday? Something that came up? Otherwise, just let me know. I mean, during these days, if you have questions, or send me emails as I said yesterday. Okay, so today we will go more into the printing technologies. I will mainly focus on 3 different types. And the question that we will have in mind is what happens with the polymers during the printing. I will show you a little bit of our results, how we try to define before we print, and also which parameter we use in order to design the printable polymer. And also what happens with the polymer during the process. And as I said yesterday, I mean, the main problem we have when we're using degradable polymers is that they degrade, right? I will give you some data on that. But just first, remind us, I mean, this thing you have in mind, but why we're actually using additive manufacturing. Why can't we just use the ordinary old techniques instead? Why do we need additive manufacturing? And I think that the customization is for medical devices and for tissue engineering is the main thing. I mean, here we can really design for space and patient-specific devices. And the next lecture we will discuss drug delivery and how we can print in order to really personalize drug delivery into pills, etc. And flexibility and on-demand. I don't know in India how it works, but in Sweden we are really trying to get the printing technology into the hospitals so that they can print either devices where they can train before they do the real operation, or something that is actually personalized that they can use. It's also from a sustainable environmental perspective good if we can have it on site, the printing technology. And it's getting there, we're getting closer, so I'm happy for that. And also allowing complexity. It's not easy to produce all medical devices and all the very tiny details using the conventional producing process methods, so then additive manufacturing can also help us there. So there are, of course, something that we want to develop further. I also want to just to mention before we go into the techniques which kind of polymers we're using. And natural polymers, I mean, from an environmentally friendly perspective. I'm sorry, I hope it was okay that we started.
Oh, no, it's okay. It's okay.
So, I mean, for example, lignin, collagen, silk, fibrin, chitosan, cellulose, alginate, hyaluronic acid. I mean, that is something that we use today while printing, for sure. But the main problem with those polymers is that, I mean, they will vary from batch to batch. And it's not that many examples of where it's actually useful today, commercially, because it varies. In comparison to when we use synthetic polymers, these are non-degradable ones, synthetic polymers that are used heavily in different medical devices. Just as an example, if we go ahead and do the synthetic polymers, but the degradable polymers, there are also many examples of where they are used. I think there are more than 150 medical devices today commercially available that use these polymers in different kind of medical devices. And this has been the research since the 80s. So there are many, and when I discuss, I will mainly focus on these ones. The polyglycolide, the polylactide, the copolymers, the polydioxanone, polycaprolactone. And I think that in comparison, when we print those, these are the most challenging one, the degradable ones, compared to the other ones that I just showed. But also, I mean, these degradable ones are used today commercially as well. There are companies that have products on the market. This is heel shape, where they use a gel, and what they do is that they try to regenerate fat tissue. So that is more a gel-based printing technique in comparison to Lattice Medical. I think that they are in clinical trials with they more form like a cage, and they also into what I discussed yesterday that we are trying to do to replace the silicone implant after breast cancer. So they use mainly polycarbonate to create this cage, and then they fill it with soft tissue that regenerate, and then by time this cage will disappear. And then Belaceno is another European company that they do different kind of tissue regeneration based scaffolds. So it is coming also commercially available, the things that we will discuss here. And I think it's good to have in mind, to be aware of that. And it's also good to be aware of the history. I won't go through the history, but I want you to remember that, I mean, when I started as a PhD student, we didn't have the 3D printing technique. And what we then used was salt leaching, mainly gas foaming, freeze drying, in order to create these porous scaffolds that we're using with the 3D printing. And in the late 80s, 1986, this Chuck Hulse filed a patent for stereolithography process. And then from then on, it has continued, and now we have a numerous number of different printing techniques. And actually, there is one technique that FDA have approved with additive manufacturing to create this pill that I will discuss later tomorrow, I think, for the drug delivery. And it was approved 2015, so it's actually 10 years ago, quite a long time we have used it. But still, even though the technique has come far, we have to understand the background and the processing details. So that is what we will focus on now. See what's actually happening. And as I said, there are numerous numbers of different techniques and different variants, and the labs create their own printing techniques and details. So it's difficult to give an overview of that. So I decided that I will focus on or present to you 3 different techniques, and that is the material extrusion. And just within that area, you have different kind of techniques as well. I will show you a little bit about the stereolithography and the powder bed fusion. And the focus will be then to understand how the polymer behaves in the 3D printer and what happens during the process. So let's start with the melting and material extrusion. So here you can choose 2 different ways. Either the one step where you just melt and print. So here is the bioplotter from Ambition Tech. I have a video soon where you see the details. We have the 3D Direct, which I think is a really interesting technique where you have the extruder in here. So you add your pellets here and then extrude, and then it's print down here. So if we're going to use pellets and print, I mean, that would be the best thing. And then you just process the polymer once. And here is from the freeformer from Arborg, where it's also an extruder, but it creates droplets onto the printing bed. And I think actually I saw that Arborg sold this freeformer now. We don't own it anymore, but that's fine for us. But totally, even though it's melting and printing, there are 3 different techniques. Or you can use the filament fabrication. So first you create the filament, and then you print it using a quite easy technique. It doesn't mean that it is easy to print, but the technique is easy. You still have many parameters to play around with, and it needs to work. And that is, I call it fused filament fabrication, and not fused deposition.
FDM.
Yeah, exactly, FDM. Do you know why? Why do I not say FDM?
Maybe where FDM is used for some rapid prototyping only for modeling, but this is for actually the fabrication of the part.
Yeah, it could be. It could be. But actually, the name FDE is trademarked by exactly. So that's why I choose to use FFF. But I mean, in literature, everyone is using FDM. Since my husband here is here, expert in patent, I need to be careful.
Yeah,
Word I
even
use.
I think this Xerox, Xerox machine.
Yeah.
Actually, yeah, that's the name.
Yeah.
And everybody said that I'm getting Xerox of the copy and all that.
Yeah, and I think Jeep as well is a word that, I mean, actually it's for one car, but we're using Jeep, the car, for many types. So I think that FDM is the same thing.
Yeah.
But it's good in any way to have in mind, right? That is actually trademark name FDM. So to be correct, we should use FFF. I haven't actually checked if it's still, I mean, if they still own the word or not. But
I
anyway.
think maybe that name they might have trademarked it, but their patent term is over in 2015 itself.
Yeah.
15 or 16 somewhere. So now anyone can use that technique and all that.
Yeah,
I don't know, but
exactly.
that name might be trademarked forever.
Yeah. Yeah, exactly. You're totally right. But here is the video of this bioplotter. I don't know if anyone have used it here, but this is what it looks like. You have so the polymer is here, and you heat it in a kind of metal cylinder, and then you print it. And then here inside you have different cylinders, so this machine can go and change to another material here. I think in a second you will see it. So what it's printing now is a silicon, which is a very easy polymer to print using this technique. It can be very detailed structure. Have you used the bioplotter?
Yeah, we do
Yep.
have that.
Ah, you have it here.
Yeah.
Okay. For the degradable polymer, I find it a bit difficult actually, because it's. I would like to have some kind of stirrer in this syringe where you heat it, because otherwise it's very difficult to melt the polymer. I don't know if you have the same experience.
When making a paste, actually, we should have Bhupesh and Ashutosh have used it extensively. So, getting a perfect paste of the, say for example, HA and TCP.
Yeah, we make HATCP paste with PVA and sometimes with other polymer also.
Yeah.
We will do perfect printing for that.
Yeah, but then you don't heat it, right? You don't
Yeah,
need to heat
we
it.
don't.
No.
We will work on normal room temperature or sometimes it's 20 degree.
Mm.
So our parameter is 20 degree, nearby 20 to 25 degree temperature, and printing speed is 2 to 5 mm per second. According to that speed, we are printed our scaffolds.
But we
Yeah.
are facing some challenge in getting the paste prepared.
Yeah, initially we are facing that paste is not homogeneous, sometimes bubbles will be formed, and extrusion will create sometimes clogging and other issues. So after multiple iteration, it will get smoother.
Yeah.
That is, initially we will face lot of issue while preparing this.
I understand. Also, perhaps from that perspective, it would be better if there were a stirrer inside that could actually.
That is homogenized mixture actually comes out.
Yeah, exactly. I don't know why they haven't done that. But this is actually what we're facing, because we cannot use the paste because we need to heat it up. I don't remember now, but over 200 degrees, and we need to use a very high pressure, the maximum pressure, in order for it to get out from the nozzle. And then what this is the reduction in molar mass compared, and here is the time. So very fast, you can see that for the polylactide, caprolactone lactide copolymer, glycolide lactide copolymer, or the glycolide DL lactide copolymer, the molar mass decreases super fast. Within a few minutes, you have, I don't know, see that you're starting with 150, and and then within a few minutes you have like 65% less in molar mass. See if I can, I can see how I can start this. But we anyway want to use this technique. So this is the same polymer using salt leaching and the bioplotter 3D printing. And you can see the enormous difference in mechanical properties. It has the same porosity as well, these scaffolds. But perhaps you want to have the soft ones, but still you can, as started saying, you can have all the details with the printed ones. And I think it's a little bit fascinating that you can get so different mechanical properties just using different processes. And I think that we need to have that in mind with the printing and using these polymers that you melt, that it become much harder. And this also influences the degradation. We produce these and then we degraded them to see how the degradation time is influenced by the processing technique. And then we have the reduction in molar mass again on the y-axis and the degradation time on the x-axis. And we have week 0 and we have week 52. And we have the bioplotter, and it's the dark blue one, the top one here, compared to when we used the salt leached one, which is the yellow one, or the Prusa. So there are differences, especially when you use the Prusa and the bioplotter in degradation time, which we also need to consider. As I said yesterday, we cannot generalize when we write papers that this is a polymer we printed like this and then it has a degradation time. And we really need to specify what we're doing and which parameters we have used and how we cannot only print and degrade, we need to also report after printing what we actually started with. And why do I bring this up? Because this is a major problem when we're coming to the regulatory issues. When using these degradable polyesters in printing. Because when in the regulatory they say that we cannot have any variation within the build cycle. We need to have a reproducible process in order to get through the regulatory issues. And today that is very difficult. But then I have a question to you. So you say that you're using this melting technique and the polyesters. How can we then minimize the degradation?
You mean to say more automation in the printing?
Yeah, that would be super. Yeah. That is actually something that I'm trying also to get money for. I mean to learn the machine, use AI or machine learning so that they can feel the viscosity and how the polymer behaves and adapt the processing parameters. I think that would be a super good solution, something that we need for these polymers. Because it's very difficult, we cannot, also by time, if you melt it and print it, by time the viscosity will get lower because it degrades, and then we need to adapt the processing parameters. And if the machine can do it themselves, that would be perfect. And I'm sure it will come, but I haven't seen it on the market yet, at least.
We have tried, hopefully Bhupesh, we have tried our best to use AI to some extent, but then again the data required to develop a model itself is big.
Yeah, you need a lot of data first.
And that too reliable data, based
Yeah.
on which we are going to train. Hopefully that is the problem.
For AI, we are using slurry data will be used for AI model generation. But while using printing data, that data must be less. We require lot of data to generate a AI model. That cannot possible while collecting printing data. So we are facing that problem.
You mean that you need more processing data in order for it
Yes,
to
more
work?
printing data.
Yeah.
Because every time we make slurry and printing it's not possible. That's why the generation generated data for 3D printing is less.
Yeah, I agree. And it's also difficult to get those data from the literature, since all machines and techniques are so different.
Yeah, in literature, everyone using different printer, so their process will be different, their material will be different.
Yeah.
So we cannot combine that data for the generation of AI models. Everyone using their own combination or own composition.
Yeah.
So that will be the problem for generating AI model in 3D.
Yeah.
See, for feature data, anyone can generate some model, but to deploy it in the practice, I think we have to test it a number of times. That's what these people are facing.
Yeah.
Maybe, I don't know how far it is relevant to what we are now discussing, but maybe in the future, if we can have a data shops, we will be selling the data.
Yeah.
I hope it will be quite interesting.
Yeah, I totally agree. And I think that we need that.
Yeah.
Different kind of databases where we can get this.
So our research will definitely get another boost.
Yeah, I agree. I agree. But what we did, since we don't have the AI yet, so what we did was to look into the rheology of the different polymers and try to see. Astrid was a PhD student of mine, and she did a huge work on this, as well as Chopin, looking into different polyester-based polymers to see the differences in rheology and see if we could correlate that with printing parameters and try in advance to see how to optimize the printing parameters and how they would behave. So we chose the most common polylactide-based copolymers, and then we made up a chart. We looked into the printing speed and the printing temperature and try to map where these polymers are. And if you just look in this chart a little bit, if we focusing on the printing temperature, if we have a high printing temperature, then of course we will reduce the viscosity and elasticity of our melt. But we risk thermal degradation if we are not below where the degradation starts to, when the polymer starts to degrade, found by DC, as we discussed yesterday. And it can also be a bit difficult to control the geometry, right? Because if you have a high viscosity, then it might be difficult for it to stabilize afterwards. But instead, if you have a low viscosity, you will get a higher viscosity and elasticity, and you, if possible in your printer, you can adapt the pressure. But for in our case, normally we use maximum pressure, so we cannot actually decrease the temperature more. And you will also risk die swell if you have lower printing temperature. If we instead look into the printing speed, if you have a high printing speed, then it might be not possible because there is a pressure limit normally in the printers. You will face die swell and also low control of the geometry because the speed is so high. But if you have a low printing speed, then you will need to keep the material for a longer time in the printer, which will then might affect the degradation. And altogether, where you will end up here depends on the polymer's melt flow, the melt elasticity, and the time, the thermal stability. So what we did was to look into the rheology. We looked into the complex viscosity, tangent, etc. And the DC, the TM, TG, the crystallization temperature. And then we mapped it. I don't go through the details for the rheology, but if you're interested, they are published, all these data. I just show you the results, how we mapped it. So we could, in this chart, map where the polymers are. And there are a few categories where you have these polymers, where PCl, if you work with that, I'm quite sure that you know that it has very high melt elasticity, but that also goes for the PLGA, which is a copolymer of clipolide and lactide, and also DL lactide. All of them has a high melt viscosity, melt elasticity, and you need to have a low speed and a high printing temperature for it to print in a good manner. in comparison to the others where you have a more viscous behavior, where you have a copolymer between lactide and TMC, 3-methyl carbonate, or the caprolactone lactide. And that also goes for the polydioxanone, which also has a more viscous behavior in comparison. All this is in comparison to polylactide itself. So we have polylactide as a reference, and then we compare the other polymers compared to that. So we could map and understand, okay, why we need higher or lower temperature, and also printing speed, and correlate them to each other. We could also look into the properties of them, where we have the polylactide TMC and polycaprolactone lactide, which are quite stiff, as well as the polycaprolactone is also stiff. The problem with polycaprolactone is that it also degrades very slowly. But the positive thing that it is thermally stable. So you can actually have a high printing temperature for the polycaprolactone without degrading it. But the degradation time is very slow, and if you want to have it in a tissue engineering medical device, it might be too long. But if you look into paradioxanone, it's less stiff and it degrades faster compared to polycaprolactone. And then we started to think, okay, but looking into this chart, perhaps we can combine the polymers a little bit here. Combining caprolactone with paradioxanone might get a less stiffer material that degrades faster. And that was our ideas after this. And then I had a postdoc that did this copolymerization, where we have the paradioxanone and we have the lactide. Created a copolymer where our ideas was then that it degrades faster, and since we have this oxygen within the paradioxanone, it's also we get the flexibility into the macromolecules. So we polymerized it in, I think it was like almost 1 kilo batch, and then we made filaments out of this polymer using FFF to print. And what we could see using the rheology was that we could place this copolymer here, where we could have quite good printing speed and quite good temperature in printing. So it was at least to the rheology, and we could also verify it later with the printing that it was printable and did not degrade using these parameters. Of course, if we can increase the temperature as well, but then you get more viscous and it starts to degrade. We could also see that it was, depending on how much caprolactone we have in the copolymer, so here it's 80% caprolactone and here is only caprolactone, the thermal stability increases. So here is, if we have 80% caprolactone, it starts to degrade around 256 degrees. And then by adding more and more caprolactone, we get a more thermally stable copolymer. So that we could also decide, okay, what printing temperature do we need and how much of the paradioxanone should we then add. And as I said, polycaprolactone has a very low degradation rate, and that can be seen here, where we have the molar mass degrees and the degradation time. And the black one on the bottom is polycaprolactone. So within 120 days, it almost doesn't degrade at all. But when we increase the amount of paradioxanone, the rate increases. And the red one is where we have added 20% of the paradioxanone in the copolymer. So we did a good study out of that and found that we could use the rheology to understand how to print, and that we could print in a way that it does not degrade. So we designed from this way a printable, thermally stable polymer that degrades faster than polycaprolactone. It would of course be more faster to use AI. It takes a couple of months to get all this data to understand. Yeah.
We are using PCL also, PCL with a ceramic composite. But we are using PCL at low temperature, not directly. PCL will be diluted in solution like DCF. While printing, I am facing some problem. While printing, Sometime it get printed, but after 10-15 minutes it get plastic like structure. So is there any reason how their chemical reaction will happen or something will change?
But only sometimes, not always, you mean, or?
No, always, but time duration will be sometime less, sometime larger. Sometime in 15 minutes, sometime in half an hour.
Yeah.
But it get plasticity.
It softens. Or what do you mean? I thought that you meant it becomes hard.
No,
No?
we are not melting it. We are diluting PCl molecules,
Yeah.
PCl granules in DCl.
Yeah.
So it get liquidity.
Yeah.
That liquidity will be mixed in a ceramic powder. So paste will be formed.
Yeah.
While printing at 20-25 degree, initially it will get printed. But after some time, 15 minutes or 20 minutes, it form a plastic-like structure that cannot be extruded from the nozzles.
In the syringe.
Yeah.
It's a clogging problem.
Clogging problem.
Yeah, I
It's
see.
due to
I see your
PCl.
point.
Because we are
But
using
have
other
you then
polymer
also
also.
removed your solvent? Or
DCl.
yeah, but do you still have the same amount of solvent, or does it evaporate? And that cannot be the reason, right?
That DCM will be stable at 20 degree, 15-20 degree. Sometimes it get evaporated. Yeah, that will say happen sometime. That may be the reason, but it get plasticide now. Plastic formation is there due to PCl.
I don't know why it happens by time. If it works, if it works in the beginning and nothing changes, it's a bit strange. What comes to my mind first is that there is evaporation of the solvent. But if that is not the case, then because 20 degrees it won't degrade, the polymer won't be influenced. For the ceramic powder, I don't have the experience, so I don't know if that could degrade in the CM environment, or that could be the issue.
In ceramic point, we are using calcium phosphate group. So PCl will react with calcium or phosphate group.
At 20 degrees.
Yeah. Due to DCM or activator any.
Is that there is a question, or you know that it will react?
My question is why this will happen? Why composition will get plasticity?
I wouldn't say that the PCl reacts with the calcium phosphate.
Ma'am, actually evaporates.
Sorry?
PCM might be evaporated and the percentage of solvent will reduce.
Yeah.
So then
I think that may be the reason.
Yeah, that would be my first guess.
because I have also tried with PCL with chloroform, so I have also got the same problem.
Chloroform will be here.
Yes, after some times it's get solid plastic structures.
Yeah, that would be my first guess. So then, this is what it looks like. Now, we actually also designed a printing structure. I will discuss that during another lecture. And using this polymer and this specific design that we patented, we started a company, Akira Science, that one of my students now is owning and running himself. And I didn't know that it was a little bit commercialized now in this video. I just took no one. But this is what it looks like. And I think it's, using polycaprolactone, I think these polymers are, these properties are really fascinating. But it's more like a silicone feeling when using this scaffold. But then it's actually based both on not only the polymer itself. The good with the polymer is that you can print it, it doesn't degrade, and then how we print it is one of the main reasons for why we get these properties. So I think, using our creativity of how to design the macromolecule, evaluate in the rheometer, we could actually reach this. And again, perhaps that is faster done with AI in the future. And just as an example of, I found this, it was in 2021, this was done in a hospital in the south part of Sweden, that they operated an FFF printed skull implant. Not using a degradable polymers is actually PEEK that they use. used. But they did it in the hospital and then they did the operations. So it is used. Moving on from the bioplotter and the FFF, we also have, I mean, we can think of extrusion-based printing also as the bioprinting, where you, I know that some of you are working with that, so some of you are very, very well aware of this technique, where you have a bio ink, and then you add, normally you add cells, and then you print it. And the Cell Link is one of the main companies here selling those printers. I won't discuss that now because the next lecture will only be on bioprinting and mainly examples of how we're using printing and which ink we're using. I would say that especially when I work with people that work from the biology side, they normally use the commercially available bio ink and not, they don't synthesize it themselves. And then it's like a black box, they really don't know what they are using. But there are many examples of synthesizing those gels as well. But I will come back to that. Going into a little bit of stereolithography, where we, instead of melting, we photopolymerize the polymers after printing using normally the UV laser that we just irradiate. I will sit down now because now I have a few movies, so you can. I won't discuss it in detail the techniques, but I just want to. Here's just the examples. I mean, normally when you use this photopolymerization, you can either use a laser, stereolithography. If you instead of using the laser, use a projector, we call it digital light processing, and then you can also use the more continuous digital light processing techniques. So just to have a look at that, so you are aware of the differences. See how this can be done. No, I don't know exactly how it works, but let's try. Perhaps I need to. Perhaps I can do like this. Yeah, it just it's, I think it's coming. I'm just gonna. Does it only work when I?
Maybe you can copy. You directly.
Why does it work when I have it on my screen?
Single click on that arrow. It's a
You can go in a presentation mode and single click on that.
But now we don't have the sound. Where did the sound?
sound. I'll do that.
Did I do something with the mic? It worked before, right? Sorry, here it is. Again. Where am I? It's difficult when you have two screens. Let's see. Yeah, I can do that. That's right. Perhaps it doesn't matter now if we have the sound or not. I can check that in the break for the next one.
Yeah,
If that's more
yeah,
important.
yeah.
Because here I think that you can understand how it works.
Yeah.
That you have a laser here and it irradiates into specific parts into this fat, and it then polymerizes. Then you get a new layer, and then the laser is irradiating again. In that way, you create. And if you're having the digital light processing, the main difference here is that instead of a laser, you're using a projector instead. Otherwise, it's quite similar. And then let's see if I can get this to work. We have the continuous digital light processing. Sound, but perhaps we can look into the movie again.
Such a complex structure.
Yeah, it is. And one of the advantages with this continuous digital light processing, I guess, is that the continuous process that can create more complex structures. So in these techniques, you're using, of course, some totally different polymers, and you need to add something that can be polymerized using laser or irradiation. Less prone to degrade, then you have other issues, I guess, with the technique, but not the degradation as such. Spending some time also on powder bed diffusion, something that we have worked a little bit with. If we can get this maybe to work. It looks like quite similar to the stereolithography that you work different. But here you have powder particles instead of the polymer. You create a layer. There is irradiation specific points, and then you add a new layer, and the laser is working, creating the structure in this way. Possible to do quite a complex structure, and it's quite used in companies. And if we look into things that is important that influence this powder bed fusion technique, we need to look into from the material properties perspective, the thermal properties of these particles, the physical properties, the particle size, particle shape, the bulk density of this powder, and the behavior, like if it's liquid or powder form. If we look into the SLS, or it used to be SLS, and now powder bed fusion is a bit, I tend to forget. But if we look into the process parameters, Of course, the laser-based parameters, the spot size, the laser power is of importance. The scan speed, scan spacing, scan strategy, how it is scanned is of importance. And also again, if it's a powder form or how the powder looks like. So also here, even though it's not the printing speed, the printing temperature, there are enormous amount of different parameters to play around with here. And perhaps something, this is just summarize this a little bit. And the most common polymers that is used in this technique for the amides, titanium peak. An application where this is used is heat implants and also different kind of personalized medicines. But the main problem with the powder bed fusion, I would say, is the surface roughness that is created here. And we will focus on that tomorrow, how to characterize. But this is something that we created in one of our projects, what the surface looks like. And just looking at it, you can see that it's not a flat surface. And this is what it looks like after powder bed fusion. So it's a very complex and porous structure when it's as printed. You need to use post-prep processing when using this technique. At least, I mean, you don't need, but if you, we want to use it in this technique in bioprocessing techniques in order to be able to create more complex structure and save time for the industry. So then we need to use post-processing. We also, in this case, and perhaps also in other cases, but be more careful of and also be more often use surface characterization to understand what the surface looks like. I don't know if when you print your scaffold, if you look into what the surface looks like, but that also influences how cells will interact, or bacteria or anything else will interact with your scaffold. So it's not only the material as such or the design, it's also actually what the surface looks like. And the problem is that today we don't do that enough carefully. And using the values today in industry, I will discuss that tomorrow, but the RA value, and that is not enough accurate method to decide if the surface is good or not. We need something better, and I will discuss that tomorrow. And also, of course, perhaps this is a good surface for some of the end applications, but not for others. So we need to have in mind actually where to use the printed scaffolds. So I think that actually is the end. I mean, for all these techniques, we could spend like a week, I think, to discuss the details. But at least for the melting part, we could get some understanding of how carefully we need to be in order to understand how the polymer behaves in the printer. And the same goes for the stereolithography and the powder-based fusion, even though I didn't have time now to go into detail there. But have that in mind, that to understand that will save time and we will be more efficient and create more better products. Comments or questions related to this?
Yes, ma'am.
Yes.
At the start of the lecture, you have told us about the in-house fabrication of implants that doctors are using, hospitals are using in Sweden. So similarly, we are doing it here also. But the problem that I faced when I work with doctors, that the number of patients that require implants are far less as compared to other treatments. So the materials that we are using, so their shelf life will be not that much fast. So the materials are remaining in a large amount, or so it is a loss for our hospitals, financial loss. So which materials we can use so that can be for their longer period of time on shelf and without affecting the properties.
But how do you keep it straight, just without any?
If we are taking all the preventive measures also, but
because if you have it in the pouch that doesn't where it doesn't get in any humidity, and also an aluminum pouch outside, it can be there for years without degrading. So I don't know if that is too short time, but I know that at least 3 years we can keep it. but you need to be careful. You cannot have it on the shelf just like that. Then it will degrade immediately and change properties. But if you carefully design the environment, then it's okay.
So any other there are preventive measures that we can take increase the shelf life?
I mean, not without changing the polymer. Of course, you can have less degradable polymers. But, and I will also show tomorrow that actually, depending on which temperature you store your polymer in, it will also influence the surface roughness. So that's also important, not only the shelf life itself, but which temperature. Because normally you can say also that we keep it in a cold environment because then it degrades more slowly, but then you will also influence, you can influence the surface roughness.
In the slide we have discussed that influence of thermal degrading while printing. So is it okay to calibrate the machine, or we focus on calibrating the materials? So on which factor we should focus more?
I would like to focus more on the machine.
Machine.
Yeah, but since I'm not an expert there, I don't know anything. I have to work with the polymers and use the machine that is available. But I'm collaborating with another colleague at KTH from the more machine engineering. So they are building new robot printers, etc. So we need to collaborate because they also need to understand the behavior of our polymers so that they can develop it further. But I mean, I think that would be the best if we had more possibilities to change the printers.
Actually, ma'am, I have one question regarding the bio-ink, but I think we have another lecture, so I will maybe that will be
later
clear.
on.
Yeah, yeah, but we'll focus on only bioprinting next. No?
Interesting point regarding the degradation. We are very much interested in the degradation part of the business. So the major issue is like the degradation rate should match with the cell proliferation.
Yeah.
So I think that's a major challenge, or rather we are not in a position to understand like how the cell is proliferating and how the degradation, whether they are matching or not. So which polymer is the best one for that? Studying in that respect.
Oh, I mean, I guess it really depends on the application. I mean, related to bone and soft tissue or breast tissue. I mean, it varies. I mean, how they should behave. And also, I think sometimes we only. I mean, it depends also on the application because when we think about tissue regeneration as such, we normally say that when as you say that the mechanical properties should decrease in the same rate as the new tissue develop. But in some cases, that I will exemplify later, when we work with a hernia mesh, right? Then we want it to be very, very strong for a longer time, and not that it decreases when the tissue regenerates, because then it will break again. So in that case, we want it to be stronger for a longer time, and then it can just disappear. So I think also that we need to be careful of, or design related to the application. So I think it can vary between that. Sometimes we want it to degrade within 2 weeks and perhaps 1 year, and then we have to design the polymers related to that. And also, but perhaps the main problem that we have, independent of the time, is that normally when you design the polymers, you have a high mechanical strength, and then suddenly when it starts to degrade, it drops, right? And I think that is something that in all cases we need to design so it decreases in a better way, and that is problematic. And that can actually be done also by using design parameters. I mean, you can have the different polymers within your device, so by time the first one degrade, and then you get another mechanical properties, and the second one degrade, and then so forth. So it doesn't only have to be with the polymer itself; it can also have to be with the design of your medical product, because it's tricky to use only one polymer and have such a detailed to degradation process. Even if you want to have it like that, but have it in mind also, perhaps it's possible, but you also want to use monomers that you can have in a clinical product. And if that is the case, you are also limited to a quite few, say 6 different monomers that you can play around with. We can synthesize other monomers and get other properties, but then the regulatory process will be enormously longer. So, I mean, there are many also here things that you need to choose. During our project that we ran for 6 years for this breast cancer development, or create this how to regenerate breast tissue. I mean, then we were stuck with these things because we wanted to do something that could be clinically available. So it's a limit, but also an advantage or whatever.
It's a perfect field of amalgamation of engineering and medicine.
Yeah, for sure. For sure. Yeah. I always say that, I mean, you need to be creative and just see from all possibilities. And then chemistry is normally, you can do that. It's not a problem, but you need to be creative and see what actually you need to do and what you need.
So we'll have a break for some 10 15 minutes.
Yeah, sure. Sure.
Is it okay?
Yeah. Let's have a break.
Yeah. We'll have a break for some 10 15 minutes. Yes. Would like to talk. Yeah, maybe.